In this lesson, we'll do a review of complex numbers since they are used a lot in quantum mechanics. What number, when squared or multiplied by itself, gives you -1? In other words, what is the square root of -1? Well, we know that the square of a positive number is a positive number. For example, positive 3 times positive 3 is positive 9. And the square of a negative number is also a positive number. For example, -3 times itself is also positive 9. So if there is a number whose square is -1, it would not be a real number. In fact, such a number is called the imaginary number. We use the letter I to represent the square root of -1. The square of the imaginary number I is -1. A complex number is defined as a sum of a real number and a real number times I. If Z is a complex number, we can write it as A plus BI, where A and B are real numbers. Here, A is called the real part of Z, and B is called the imaginary part of Z. For example, suppose Z equals 3 minus 2I. What are the real and imaginary parts of Z? Well, if Z is equal to 3 minus 2I, we can write it as 3 plus -2I. Therefore, the real part of Z is 3, and the imaginary part is -2. Note that what we call the imaginary part is actually a real number. It is the real number that is multiplied by the imaginary number I. True or false? A real number is also a complex number. We said that a complex number can be represented as A plus BI, where A and B are real numbers. So let's say the complex number Z is equal to A plus BI. What if B is equal to 0? Then Z will be equal to A plus 0 times I. But 0 times I is just 0. So if B equals 0, Z will just be equal to A, which is a real number. In other words, a real number is a complex number whose imaginary part happens to be 0. Therefore, it is true that any real number is also a complex number. Here's a geometric analogy that we can use to visualize the relationship between complex and real numbers. Think of a complex number as a point on a plane, which we call the complex plane. A real number would then be a point on the x-axis of the complex plane. In the example shown here, complex number Z is represented by this point. The x-coordinate of this point is the real part of Z, and the y-coordinate is the imaginary part. If you have a point that is on the x-axis, then its y-coordinate is 0, so its imaginary part is 0, and we say that this point represents a real number. For the complex plane, we refer to the x or horizontal axis as the real axis and label it with RE instead of x, and we refer to the vertical or y-axis as the imaginary axis and label it with IM instead of y. Given that Z is equal to 2, what is the imaginary part of Z? We can write Z as 2 plus 0 times I. Therefore, the real part of Z is 2, and the imaginary part is 0. The complex conjugate of a complex number is obtained by replacing I by -I. In other words, if complex number Z is equal to A plus BI, its complex conjugate, which we write as Z star, is A minus BI. For example, what is the complex conjugate of 2 minus 3I? To get the complex conjugate, we replace I by -I, and we get Z star equals 2 minus 3 times -I. Simplifying, we get Z star equals 2 plus 3I. Which of the points below represents the complex conjugate of z if z is 2 minus 2i? Here's z. Its imaginary part is negative 2, so it's located in the bottom half of the complex plane, below the x-axis. Complex conjugates basically differ in the algebraic sign of the imaginary part. In this case, the complex conjugate is 2 plus 2i. The imaginary part is positive 2, so it would be located above the x-axis. The real part of z is positive 2, so it's located on the right half of the complex plane, on the right side of the y-axis. The same is true for its complex conjugate. Complex conjugates have the same real part. Therefore, of the points shown here, point A corresponds to the complex conjugate of z. On a complex plane, complex conjugates would mirror each other across the x-axis. Suppose z is equal to negative 5. What is its complex conjugate? We can write z as negative 5 plus 0 times I. And its complex conjugate, z star, is negative 5 plus 0 times negative I, which we can just simplify to negative 5. In general, we say that the complex conjugate of a real number is itself. In other words, if z is real, then z star is equal to z. Conversely, if z star is equal to z, then z is real. Which of these is not equal to the other three? I star, negative I, 1 over I, or I star times I. Let's take a look at choice A. Remember that to get the complex conjugate, we simply replace I by negative I. Therefore, I star is equal to negative I. This means that choices A and B are equal. Let's take a look at choice D, I star times I. We replace I star by negative I. Then, I times I equals I squared. So we have negative I squared. But by definition, I squared is negative 1, so we have negative of negative 1, which is positive 1. This means choice D is not equal to choices A and B and has to be the correct answer. What about choice C? We need to get rid of the I in the denominator. To do that, we multiply it by I star. We must also multiply the numerator by I star if we don't want to change the value. Now we simplify. I star in the numerator is just negative I. And we have already seen from choice D that I times I star is equal to positive 1. So our denominator is positive 1. Negative I divided by positive 1 is just negative I, which means choice C, 1 over I, is also equal to negative I, just like choices A and B. If we multiply a complex number by its complex conjugate, and then take the square root, we get its absolute value. In other words, the absolute value of complex number z is equal to the square root of z star times z. Because of this, we refer to z star times z as the square of the absolute value. So, if z is equal to a plus bi, how do we determine its absolute value? Well, we know z star is a minus bi. Therefore, z star times z is equal to a minus bi times a plus bi. This is just a product of a difference of two things and their sum. We know from algebra that this would be equal to the difference in the squares. So, a minus bi times a plus bi is equal to a squared minus bi squared. Since I squared is negative 1, this expression simplifies to a squared plus b squared. Therefore, the absolute value of z is the square root of the sum of a squared and b squared. If z is equal to 4 minus 3i, what is the absolute value of z? The absolute value is equal to the square root of a squared plus b squared. The real part a is 4. The imaginary part b is negative 3. So absolute value of z is equal to the square root of 4 squared plus negative 3 squared. The absolute value is 5. Let's locate this number on the complex plane. Here's the real axis. Here's the imaginary axis. Here's the point that corresponds to z. Its real part is 4. Its imaginary part is negative 3. We can see that we have a right triangle here with sides of length 4 and 3. According to the Pythagorean theorem, the length of the hypotenuse is 5. We can see that the absolute value of a complex number is just its distance from the origin. This also means that all points on a circle centered on the origin represents complex numbers with the same absolute value. Suppose complex number z is given by a plus bi. We can represent z as a point with coordinates a, b on the complex plane. This length is equal to the absolute value of the real part a, and this length is equal to the absolute value of the imaginary part b. We can see that the absolute value of z is just the length of the line segment from the origin to point AB, and we can calculate it as the square root of a squared plus b squared. Now consider the angle between the real axis and the line segment from the origin to point AB. If we call this angle theta, it's easy to see that cosine of theta is a divided by the absolute value of z. So a is equal to absolute value of z times cosine of theta. Similarly, it's easy to see that b is equal to the absolute value of z times the sine of theta. Replacing a and b in the expression for z, we get z is equal to absolute value of z times cosine theta plus absolute value of z times sine theta times I. Factoring out absolute value of z, we get z is equal to absolute value of z times the sum of cosine theta plus I times the sine of theta. This sum of cosine theta and I times sine theta can be shown to be equal to e raised to the power I times theta. So here we have an alternative way of expressing a complex number. Z is equal to its absolute value times e to the power I times theta. Instead of expressing it in terms of its real and imaginary parts, we can express a complex number in terms of its absolute value and theta, which is called the phase angle. Either way, we need two numbers to express it. If z is equal to 3 times e to the negative I times pi over 2, calculate the real and imaginary parts of z. The absolute value is 3. The phase angle theta is negative pi over 2. So we can calculate the real part as absolute value of z times cosine of theta, and cosine of negative pi over 2 is 0. So a is equal to 0. Similarly, we can calculate the imaginary part as absolute value of z times the sine of theta. Sine of negative pi over 2 is negative 1. 3 times negative 1 is negative 3. Let's locate this number on the complex plane. Here's the real axis. Here's the imaginary axis. Here's the point corresponding to the complex number. The real part is 0 and the imaginary part is negative 3. You can see that it is 3 units away from the origin. Here's the line between z and the origin. The angle between this line and the positive x-axis is negative 90 degrees or negative pi over 2 radians, as expected. By convention, we assign negative values for angles measured in a clockwise direction from the positive x-axis. If z is equal to negative 5, what are the absolute value and phase of z? We can write z as negative 5 plus 0 times I. Therefore, the complex conjugate is negative 5 plus 0 times negative I. It's also equal to negative 5. Remember that the complex conjugate of a real number is itself. Therefore, the square of the absolute value, z star times z, is equal to positive 25. And the absolute value is a positive square root of 25, which is positive 5. The absolute value of negative 5 is positive 5. Of course, you didn't have to learn about complex numbers to know this. The point here is to show that the definition of absolute value for complex numbers is consistent with the definition of absolute value for real numbers. Where's 5 on the complex plane? Here's the real axis, here's the imaginary axis, and here's negative 5. It's located at negative 5, 0. It's 5 units away from the origin, since its absolute value is 5. It's left of the origin, since it is negative. It is on the x-axis, since it's a real number. The imaginary part is 0. So what is the phase angle? Here's the line segment joining the point corresponding to z and the origin. The angle that it makes with the positive x-axis is 180 degrees, or pi radians. Negative real numbers have phase angle of 180 degrees or pi radians. What would be the phase angle for positive real numbers? The point would be located on the positive x-axis of the complex plane, so the phase angle would be 0. Taking the complex conjugate of a function simply means replacing all instances of I in the expression for the function by negative I, and every variable and symbol in the expression by their complex conjugate. For example, if f of x is ix divided by 3 plus 2i, then how would you write the complex conjugate of f? You'd write it this way. Replace I by negative I, and replace x by its complex conjugate, x star. If a variable or symbol represents a real number, then its complex conjugate is itself. For example, if x happens to be real, then you don't need to put a star on the x. The relationship e to the ix equals cosine x plus I sine x is known as the Euler formula. This is a very useful formula to know in quantum mechanics. From this, it should be straightforward to show that cosine x is equal to 1/2 times the sum of e to the ix and e to the negative ix. Similarly, you can show that sine of x is equal to 1 over 2i times e to the ix minus e to the negative ix. These formulas will allow us to construct functions that do not have imaginary components from functions that do. Euler's formula can be derived from the power series expansions of e to the x, cosine x, and sine x. You should be able to find several videos online that can help you with the derivation.